So, welcome my friends, welcome to my next lecture. So, now this lecture I plan to talk about what is called, of course in my last lecture I talked about double integral and triple integral. So, now this is a new concept I will talk about. So, of course I need couple of lectures. So, today is the first lecture for that. So, as you see in the title, it is gradient, like gradient, divergence, curl, Laplacians. So, those are the new concept. So, in multivariable calculus, so I will start with that. Of course, I think gradient you might be familiar with earlier. So, the divergence, curl, Laplacian. So, these are the concepts I will talk about that from this lecture onwards. So, next coming few lectures I will have those kind of notions. Okay, so that's what I have written. So, what is the learning outcome for upcoming couple of lectures? So, first to talk about like what is called divergence, curl, or say gradient or vector field, gradient, whatever it is. So, I think not whatever it is, but I think those concepts. So, I need the first of all the concept what is called vector field. Okay, so that's I have written. So, like what is vector field? So, I will introduce the notion of vector field. Then I will give couple of examples like visualizing vector fields. What is vector fields? Couple of examples. That means you can visualize your vector fields like sample arrows or integral curves or equipotential curves or surfaces method. So, these are the three things I will discuss. So, then there will be a new operator what is called del operator, okay, that I will talk about that. Then gradient you are familiar with, I already talked about that. Given a functions from Rn to R, say scalar field, then you know, in fact Rn to Rm you have the notions of gradient of f. In fact, the scalar field I already discussed. So, then there is a kind of, if I have a vector field, then there is a notion of what is called path independence. Then I will talk about what is called conservative vector field. Then there is a notion of gradient vector field. Then I will talk about divergence and curl, and of course, I will talk about vector potential of a vector field, and at the end I will talk about what is called Laplace operator. So, this is the kind of quick plan of upcoming couple of lectures. So, mainly I will focus on like divergence, curl, Laplace operators, and then once I have a vector field, then corresponding notions of divergence. So, these are the things I will talk about that. Okay, let me start with the concept what is called vectors fields and visualization of vectors fields. So, what is vectors field? Let me start with the definition first. Okay, so the vector field, it says that suppose I am in say n dimensional Euclidean space, and suppose you have a domain D. Okay, so suppose you have a Rn and you have a suppose some domain D. Vector field, you can see if I take any point in the domain, what I will do, I will associate a vector on that point. So, that's exactly I have written. Look, let D be a region in Rn. If each point P in the region D, a vector that I am denoting as f of P is assigned. So, that means, so suppose this is my Rn, of course, this is my R2, suppose I have a domain D. So, each point I will have a vector, each point I will have a vector. So, that kind of things I am doing. So, that means for each point P in the region, a vector that I denoting as f of P is assigned. The collection of all such vectors is called the vector field on D. Okay. So, therefore, I have a Rn, suppose I am starting with a domain D, okay, some D, nice domain, and what I am doing, I am considering a point in that domain and then I am associating a vector, okay, and I am doing it for each point. Then the collection of such vectors is called the what is called vector field. So, that is the kind of idea, and in terms of definitions what I am writing, the definition says that a vector field in Rn is a function that associates a unique vector f of P with each point P in a region D subset of Rn. So, that means what is going on, suppose I have a domain D in Rn. So, then I am, suppose I have a function capital F, say from D to Rn, D, where D is a subset. So, that means I can write it capital F, this is D. So, this is D subset of Rn to Rn. Okay. So, that means if I have each point P is, it goes to f of P. And what is f of P? F of P is also a point in Rn. So, that means what I am doing is that, so I am thinking about Fp, which is a unique vector. In fact, I am associating with the point P. That means I am somehow, I have a point P, I have a point Fp. So, a vector starting point P and end point is Fp. So, that is the vector I am talking about. So, that exactly the things. So, a vector field in Rn is a functions that associate a unique vector, of course. For each point in the domain, I will have a unique vector Fp with each point P in a region D in Rn. If that is the case, then I will say that this is a vector field. For example, let us see the example like for this functions f of x y, which is minus y times I cap plus x times j cap. So, that means what is that? This function is from R2 to R2, this is a function is from R2 to R2. Okay. Now, for each R2 point x comma y, it actually goes to minus y comma x. So, that is what it is doing. Okay. So, that means if I have a point x y, so this is the mapping minus y to x. So, but minus y to x, that means the corresponding point x y, I will associating a vector, and that the vector which starting point is x y and end point is minus y comma x. I will give some pictures, then it will be more clear what do I mean that associating a vector with each point in the domain, then it is called a vector field. So, this is a vector field capital F. Another example gxy, which is 2x times I cap, while x is running from 0 to 1, y is running from 0 to 1. Of course, here I am specifying my domain is the square, right, while x running from 0 to 1 and y running from 0 to 1. So, that means this is the domain I am talking about, this is the domain. So, this is 1 comma 0, this is 0 comma 1 and this is 1 comma 1. So, this is the domain I am talking about. Each point I am associating a vector. Which is the vector? Vector is 2x cap. Okay. Then this is another example capital H, which is minus y I cap plus x j cap plus z. So, z coordinate I am keeping as it is and xy coordinate I am flipping right this one. Okay. Of course, you are familiar with the gravitational vector field capital F of r, which is nothing but minus m times capital M capital G, then you have r by r modulus of r cube, that means norm of r cube. And what is r? R is the point in the space like x comma y comma z. Okay. Then I will talk about that if I have any scalar field, that means if I have a functions from Rn to R, then if you remember that gradient of f is a functions from Rn to Rn, right, and then gradient of f is actually a vector field. Okay. So, for a given scalar field, that means given a functions f from say Rn to R, I already explained that if I take the grad of f, it is a map from what is called Rn to Rn, and this will give you a what is called a vector field. So, that sometimes f is called the potential and this is called the gradient of f is called the vector field of this potential. Okay. And whatever the last one, these are plenty of examples. So, a couple of examples I am talking about. So, for any smooth curve C, RT is the corresponding parameterizations and then R prime of T is a vector field on C. So, now what is that? So, suppose you have a curve in say R2, like means if I draw it like, so suppose this is the curve, okay, or this is a curve and let it be C. So, C will have a parameterization, right. So, that means you will have a functions capital R from closed interval AB to R2, okay, and that will give you some curve in R2. And what I am doing, I am considering R prime T. R prime T means what? So, if I take a point RT in the curve, R prime T is nothing but the tangent at that point. So, suppose this is my point RT, okay, this is. So, this is the vector I am associating, that means R prime T, that means the tangent vector at that point RT I am associating. So, if I take this point, so that means this is the tangent. So, if I have this point, this is the tangent. So, that means each point I am associating a tangent. So, therefore, R prime of T is actually a vector field on C. Okay. So, therefore, R prime of T is a vector field on C, because C is a subset of R2. R prime T, what is R prime? R prime is a map. So, that means I should say that what is the vector field? Vector field should be F is a map from C to, which is C subset of R2 to R2. Okay. And what is that? F of RT. Like, because for each T, RT is the parameterization, right. So, for each T, RT is a point in C, and what is the vector field capital F? F of RT is nothing but R prime of T. So, that means the corresponding vector I am assigning at the point RT in the curve C is nothing but the tangent vector. So, that means this R prime T that I am saying that the corresponding vector field is capital F, which is a map from the subset C subset of R2 to R2, and C has a parameterization R. Okay. So, therefore, for each point RT in C, I am associating a vector which is nothing but that R prime of T, which is nothing but the tangent vector. So, therefore, for each point in the curve, I am associating a tangent vector, and this will give you a what is called vector field on C. Okay. So, for each point I am associating a vector. Okay. I will give some example that will be more clear. Okay. Okay, so before that, maybe I think I just say a little bit about that. Look, vector field, that means what? So, that means if I talk about vector field, that means it associate a function, right. So, if I want to talk about a vector field on some domain subset of Rn, that means I am talking about a function from your domain D subset of Rn to Rn, because I am talking about a vector. I mean, it should be a point in Rn, right? So that means I am talking about a functions. And what vector I am associating? So given a point P in the domain in D, I am associating a vector f of P in that point P, and what is that vector? It starts with the point P and ends up to f of P. So this is the vector I am associating. In other words, I have a functions f from set D subset of Rn to Rn, where P goes to f of P. So that is the definition of vector field, right? So vector field, that's exactly I have written. Vector field is basically a functions from D subset of Rn into Rn, but there is a subtle difference between vector field in Rn and vector function from Rn to Rn. Okay, so Rn to Rn function means what? If I have a point in Rn, then you will have a point in Rn. So that is the functions. Vector field, which is nothing but a functions, but it has some extra geometrical features. What is that? That's exactly I have written. In other words, a vector field is a specific type of vector valued functions. So not all vector valued function, it's a specific type of vector valued functions with a geometric interpretations. And what is the geometric interpretations? In other words, it assigns a vector to each point in a space, and that vectors is understood to be associated with or attached to that specific point. So that means I have a functions capital F from D subset of Rn to Rn. If I take a point P in D, I associate the corresponding map is F capital F of P in Rn. And what is the vector? I am talking about the vector P to Fp, that means starting with P and ending with Fp. So this is the vector I am associating or attaching with the point P. So, and that's exactly I have written. So a general vector valued functions from Rn to Rn does not necessarily have its geometric connections. So that means I am considering the functions, of course I am talking about the functions from Rn or some domain Rn to Rn with some geometric interpretation. So that's the subtle difference between the functions, vector functions from Rn to Rn and the vector field. Okay. Again the same thing I have written. So geometrically a vector field capital F on your domain D is interpreted as attaching a vector to each point of D. At each point P of D, a vector that starts at the point P with the magnitude and directions of Fp is drawn or associated, right? Now it is clear. So if I take a point P in the domain, so I am associating a vector. So there is a function, right? Capital F from D subset of Rn to Rn. Suppose P maps to F of capital F of P. So P maps to F of capital P, and the vector I am associating with the point P, that's exactly I have written, a vector that starts with the point, I am associating with the point P, starts with the point P with the magnitude and the directions of Fp. So corresponding F goes to Fp, so that is the vector I am associating. One example if I give you, then it will be more clear. For example, this is the vector field I want to talk about. What is that vector field? So it's a map from R2 to R2, right? X comma y. So it is x comma y maps to what? Minus y comma x. Okay. So therefore it's a functions. Now it's see there is a geometrical interpretation. So what is that? So draw a vector field at the sample points 1 0 0 1 minus 1 0 and 0 minus 1. It will be clear what is going on. Okay. So first of all, this is a map. It is a map from R2 to R2, and how it maps x y goes to minus y comma x. So now let's see. I have 4 basic points I have given. So let me draw a picture here. Okay. For example, there is a very small place. Okay. So let me draw it here. So suppose this is my point 1 0, if one point is enough. Okay. Now, so this is a point in R2. Okay. So that means this is a point in D. Here D is actually full R2. Now under this map 1 0 goes to where? 1 0 goes to where? So y is 0. That means this should be 0 comma 1, right? Okay. So that means 1 0 maps to 0 comma 1. So that means this is my 0 comma 1, right? So that means I am associating a vector. Okay. So I am associating a vector at the point 1 0, and this is actually what? Minus y times I cap plus x times j cap. So here y is equal, so that means minus y, that means it should be 0 and this should be 1. That means at the point 1 0 I am associating, this is the vector, sorry. So that means this is my 1 0, this is my point, and this is the vector I am associating, yes, right. So this is the vector. So this is my 0 1 point. So I am associating at the point 1 0 the vector with this direction. So at 1 0 this is 0 1, that means I am attaching, of course you see. So that means I have to attach a vector with the point 1 0. Okay, that is the point 1 0 I am attaching, and the direction should be f of p. What is the direction? 0, 1. So that means I have a point 0, 1, that is the corresponding thing. So the direction means in the directions of 0, 1. 0, 1 means in this direction. So that means the parallel one. That means I am just translating the image f of p, that means 0, 1 in the kind of point. So this is actually, it's giving you 0, 1. That means this is the one direction it is giving, right, with the corresponding magnitude. What I am doing, I am translating it or attaching to the point given in the domain. So that means that at the point 1, 0, this is the vector I am talking about. Okay, so that's the exactly one. So that is the point, that is exactly I am doing. That means given a point 1, 0, I am attaching a vector from the point P with the directions of f of p and the magnitude. So directions means at 0, 1, this is the direction. So that means that direction with the same magnitude. Okay, this is at the point 1, 0. What will happen at the point 0, 1? Let's see. So 0, 1 means this is the point, right? This is the point. Now what is the image? So now look, the function is xy goes to minus yx. So that means 0, 1 goes to where? 0, 1, that means x is 0 and y, so that means this should be minus 1, 0. And what is the minus 1, 0 point? So this is the point, minus 1, 0. This is the direction. So that means at this point I am talking about this is the vector, right? So with the corresponding magnitude and direction should be this. So that means I am just translating this vector up to this point because I want to associate a vector with the given point in the domain. So this is the one. So that means at 1, 0 you have this vector, at 0, 1 you have this vector. Now you can guess at minus 1, 0 which vector? This is the vector, and at 0, minus 1 this vector. So that means what is going on at 1, 0 means what? So that means 1, 0, if I take a point 1, 0 in the domain, so I mean this is the vector. What I am doing at 1, 0, I am associating a vector here. So that means actually this is the vector I am actually rotating in an angle of pi by 2. Similarly here, so this is the point, so this is my direction, so this is my direction, I am rotating by pi by 2. Again this is the direction, I am rotating by pi by 2, and that is exactly I have written. You can see this vector field rotates a vector. So this is my vector, right, domain. If I take the 1, 0, so that means this is the vector I am talking about, right. Now what is the vector I am associating at the point 1, 0? This is the vector. That means I am somehow rotating my 1, 0 vector in an angle pi by 2, I am getting this one. So that's exactly I have written, a vector in the anticlockwise direction by an angle pi by 2, and this is for 1, 0, 0, 1, minus 1, 0 and 0, minus 1. You can see any vector, that's exactly it is going on actually. Okay, so this vector field sometimes is called the what is called rotational vector field. Okay, so that means given a functions, of course vector field means it gives a functions from R2 to R2, but this time it will have some geometrical interpretation. That means at each point I am associating a vector, and how this exactly clear from this example. So that means if I have xy corresponding minus y comma x I am getting, so then what a minus y comma x means it's a point in R2, so that means the corresponding direction I am getting, and then I have to associate that vector with the point xy, then I am just translating that vector into that point. So that means in that point in the domain I am associating a vector, and that will give you what is called vector field. Okay, so this is only 4 specific points I have drawn. So that's 1, 0 you have this vector, 0, 1 you have this vector, and then you have minus 1 comma 0 this vector, and what is called 0 comma minus 1, this is the point 0 comma minus 1, you have this vector, right. So if I have all the points, I think next slide it will have, you will have the exact scenario of what sort of rotational vector field is. Let me see. Okay, now before that so I think it's clear from the example that what do I mean by the vector field. That means I am associating a domain is called a domain subset of Rn is called a vector field. That means I am associating each point in D a specific vector in that domain D with starting point is P, and that exactly I have written in this way. A vector field f on D is interpreted as attaching a vector to each point of D. That means at each point P of D, a vector that starts with the point P with the magnitude and directions of capital AP is drawn or associated. Okay, so that's the definition of vector field. Now I can visualize my vector field in 3 ways. So what are the ways? One is sample arrows. Second one is integral curves. Okay, you can calculate, there are how to calculate integral curves. And the third one is equipotential surfaces or curves. So what are those? So that's why I have written 3 different ways to visualize a vector field capital F on a region D. So first one, so it says that sample arrows. So sample arrows means what? So we take a sample points. Okay, so you have a domain D, take up sample points, and at each point P of the sample, so that means you have a sample points in your domain D, let it P is a sample points. Then what you do, we draw or imagine or arrow, that means I draw a vector PQ. And what is the vector PQ? So because it is a functions vector field, that means given P maps to, so this P maps to capital F of P, right. So this is a functions D subset of say Rn to Rn, right. So that means P maps to F of P. So that means I am associating or a vector which I am denoting as PQ at the point P, which is nothing but F of P. And these arrows has its tail. This is very important. These arrows has tails at P. That means it should join from the point P. This is my P. Okay. So that's how sample arrows, in terms of sample arrows. So take couple of sample points, and in that way you can what is called draw your, or I can visualize my vector field. So you take a sample points, then like for example rotational vector field. So that means you have a, of course it is defined on full R2, but I am taking sample points like 1 0, 0 1, minus 1 0 and 0 minus 1, and then I just use the definitions of the rotational vector field and I am associating arrows. Arrows mean the vector. So at 1 0 you have this vector, 0 1 you have that vector, minus 1 0 this vector, and 0 minus 1 you have that vector. So that means this is the kind of sample arrows I can visualize. If you draw in this way, or I can understand, okay, this is the vector field you want to talk about. Second one is the integral graphs. What is that? It says that for a continuously differentiable vector field. Continuously differentiable vector field means what? Of course, vector field is a functions from some domain D subset of Rn to Rn. Continuously differentiable means it should be in a class what is called C1. If you remember, there is a class I have called C1. That means function should be differentiable and the derivative should be continuous. That is called continuously differentiable. So for a continuously differentiable vector field, if my vector field capital E, it is a functions from D subset of Rn to Rn. If capital F is a member in C1, then I will say that it is a continuously differentiable vector field. We draw several integral curve. I will draw a several integral curve passing through the point P in D, for which my F of P is non-zero. Okay. So that means what it says is that, so you have a vector field F from domain D subset of Rn to Rn. It is a functions. It will have a geometric interpretation. That means at each point P, I am associating a vector that I am denoting as PQ, or PQ vector is nothing but capital F of P with the same direction and magnitude. If that is the case, if my capital F, since it is a functions from Rn to Rn, if it belongs to C1, that means if it is continuously differentiable, then what I can do, I can draw several integral curves through a point P inside my domain D, for which point, that point I am drawing an integral graph such that F of P is non-zero. You can do that. In fact, next slide I will talk about, that means given I will specify a kind of specific vector field, and I will say that, and I will tell you that, okay, how to get the integral graph. Either you have to just solve the differential equations, you will get it. Okay. So that is one in terms of integral curves. So if I know the integral curves at each point, the directions, then I can say that, okay, that's how the corresponding vector field, that's a visualization. In that way I can also see, instead of giving the arrows at each point, what I will do, at each point I will draw a integral curves, and with the integral curves I can say that, okay, this is the vector field I want to talk about. And third one is the what is called equipotential surfaces and curves. And what is that? It says that for a gradient field means what? Suppose I have a functions f scalar field I have, say from say R3 to R or R2 to R, suppose I have a scalar field. Then as I said, if I take the gradient, it will be a vector field, right? So that means that vector field actually called gradient field. Okay. So therefore, given a potential P or scalar field f from R3 to R or R2 to R or say Rn to R, if I take the gradient, it will be a gradient vector field. The level surface, I already talked about level surfaces of a gradient. If you remember, in my last couple of lectures, I talked about level surfaces, and if I am in R2, it is actually level curves. So the level surfaces in R3 or level curves in R2, if I want to talk about in R3 and R2 of the scalar potential or scalar field, provide another way of visualize F. These surfaces or curves are called the equipotential surfaces or curves for the field F. So this one, last one is that actually for special type of vector field I am talking about. That means that is called the gradient vector field. That means you start with a scalar potential or scalar field, you take the gradient, it will be a vector field, and then you know what is the corresponding meaning of level surfaces. If I am in R3, it is level surfaces. If I am in R2, that is called level curve. Now you can draw a level surfaces and level curve, and with that you can visualize your what is called vector field capital F, which is nothing but grad of F. So this is the last one, and those kind of surfaces and curves I called, which is called equipotential surfaces or curves. So right, three ways you can take few sample points, draw arrows. In this way I can visualize. Second one is that, okay, if I have a vector field and it is continuously differentiable, that is very important, that means it should be C1. If that is the case, then at each point in the domain I can draw integral curve. I will tell you how to calculate the integral curve for a special case if I have a given vector field. So once I draw integral curve, with that also I can, because I can draw integral curves for each point in your domain, means I can visualize what vector field I want to talk about. And the third one is that, which is very special case, that means I am talking about gradient vector field. That means start with a what is called scalar field, take the gradient, it is a vector field, and you know for a given scalar field, you know what is called level surfaces, right? For the gradient of f, you should know the level surfaces or level curve. Those surfaces and curves also called equipotential surfaces and curves of this field, and through which you can visualize your corresponding vector field. Okay. Okay, as I said, so now let's see some examples, then it will be more clear what do I mean by vector field and how to visualize it. Look, so sample errors method of visualizing in two-dimensional vector fields. Look, so suppose this is a vector field in R2, so that means you have a functions f from say R2 to R2. That means for each point, take a sample point. So these are the sample point, these are the sample point, right? So the vector field means for each point I am associating this vector. Each point this is. So this is the corresponding vector field. For each point I am associating a vector, so that means it is sample points, couple of points I have taken, not all. So that will give you the vector field in R2. What is the vector field in R3 dimensions? Again do the same thing. So these are the sample points, so each point you have the corresponding vector in R3. So that's the what is called sample arrows method of visualizing. Now this one, as I just discussed, so look. So this is the corresponding what? So this is the corresponding vector field f of xy, which maps to minus y comma x. So this is the map from R2 to R2, right? And at each xy, I am associating a vector with the direction minus y comma x and the same magnitude, right? So look, so I already discussed at 1 0, this is the sample point, 1 0 I am associating this vector. At what is 0 comma 1, I am associating this vector. At this point I am associating this vector, at this point. So this is very sample point. Similarly, if I have go to this point, I am associating this vector. If I have this point, so now you can at least guess. So if I have take this point, that means you just draw origin from the origin. That means this is the direction you will have. As I said, this is a rotational vector field. That means this is the corresponding vector you are associating. That means move your vector in pi by 2 angle. So that means this is pi by 2. So that means this is the vector you are associating. Okay. Similarly, if I take this point. So what is the direction of this point? Draw origin from this point. So this is the directions. Now rotational vector field means what? At that point you associate a vector just rotating your vector in the pi by 2. So this just rotate it. So at this point, so this is the direction, so I am associating this, so pi by 2. So this is the vector field or rotational vector field. There is a sample arrows. Take couple of points, samples, and draw that this point which vector you are associating. So now couple of points I can easily guess. So each point what you are doing, the corresponding directions you are just taking the pi by 2 and you are associating a vector. Of course, the modulus should be like minus y comma x. Directions, of course, you have to just the vector you have taken in the domain, whatever direction you will have, you just take the pi by 2. You just rotate it anti-clockwise in the pi by 2 angle, then the direction you will get, and your what is called magnitude is minus y comma x, the same magnitude as x comma y. Okay. So that's the kind of sample arrows visualizations of two-dimensional vector fields. Let's see another example. Yeah. Now sample arrows of two-dimensional vector fields. Now this time what? This time again I have too many samples. So that is why it will be like that. For example, if I have a vector field which map x comma y goes to x divided by square root of x square plus y square and y divided by square root of x square plus y square. So therefore the, oh sorry, no, this is not the case. So this is wrong actually. This is wrong. So what I am saying is that, so it actually this is the vector field. What is that? I mean x comma y maps to x comma y. This is the one actually x comma y maps to this. This is the one x comma y maps to y comma x, and this is the one x comma y maps to y minus y comma x. Okay. So that means if I have this kind of vector fields, okay. So of course these are functions from R2 to R2, and at each point I am associating a vector. For example, x comma y, that means at each vector I am associating this vector. These are the vector. So for if I have this one, this map, then for each point the corresponding vector is like this is the one, this is the one, this. And y comma x. So now you will have this kind of directions. Okay, I will just flip it, x comma y flip to y comma x. That means at each point you will have association of this vector, and minus y comma x, as I said, it is actually kind of this 90-degree things rotational. That means for each vector I am associating this vector. Okay. So, that is kind of sample arrows of visualizing of 2D vector fields. Okay. Okay, so I just draw a picture. So, this is sample arrows method of visualizing 2D vector fields. Again, you see, like if I have a what is called thunderstorm and something like that, then you will see those kind of pictures you might have seen in TVs and these things. So, this is I can just draw some pictorial things. That means for each point in the space I am associating a vector for each point. So, this is an example of a vector field. Okay. Okay, another sample arrows in the 3-dimensional vector fields. So, now again, so for each point is a sample point. So, this is the corresponding vector field. This is x comma y comma z is nothing but z times k cap. That means maps, what is the corresponding map from R3 to R3, x comma y comma z maps to 0 comma 0 comma z. So, if that is the case, then corresponding the point I am associating this vector, this vector, this vector, this vector. Fine. So, this is the corresponding figure. Similarly, if I have like x comma y comma z maps to y z x. So, kind of I am flipping the corresponding coordinate things. So, this is the corresponding what is called arrows method of visualizing. That means at each point I am associating a vector. For this point I am associating this, from this point I am associating this, from this point I am associating this. This is the one. Similarly, you will have this map like here x comma y comma z maps to y minus to x. Okay. So, if I have this one, then at each point I am associating a vector. So, this is the corresponding, that means that is the vector field I want to talk about. By looking at arrows, you will have this kind of meaning. Okay, few more examples. So, this is again 3D vector fields. At each point I am associating a vector. Okay. Similarly, here also I am associating a vector at each point. So, these are the kind of examples of vector field. That means for each point in the domain I am associating a vector with starting point in P, and what is the direction? Direction should be Fp with the magnitude. Okay. So, now as I said, so arrows visualizing, you know, now there is another way you can visualize vector field, what is called integral curves. Okay. So, what is integral curves of a vector field? So, it is the definitions. It says that, okay, let capital F be a vector field in a domain D, an oriented smooth curve C, okay, and that corresponding RT is a parameterization. Suppose RT is the parameterization, that means oriented smooth curve C in your domain D is called the integral curve of your vector field capital F if for every point P on your curve C, Fp should be non-zero. That is the first one. And second one, Fp has the same directions as the unit tangent vector Tp to C at P. Okay. So, that means for like if I draw a curve in say again R2. So, that means this is the curve in R2, right. So, it will have a parameterization, let it be C curve. So, suppose this is my parameterization RT. Okay. So, what I am saying is that what is the integral curve? Integral curve is that it is nothing but a oriented smooth curve. So, look, I have a vector field something. So, an oriented smooth curve, let it be C, and which is parameterized by RT in your domain. So, that means I have a domain. So, I have a domain, this is my domain. Okay. So, this is C, and I will call that this is the integral curve of your vector field capital A if at each point P. Now, if I take a point P in C, how it looks like? Of course, it should be like R of T, right? That is the point P in C, right? Because I have a curve C, I have a parameterization RT. If I talk about a point in your domain D, in particular it is a point in your curve C, I mean it is of the form RT, right? So, what I am doing is that f of P should be non-zero. If it is an integral curve, that curve C is an integral curve, and Fp, that means the point P goes maps to f of P, that is the corresponding vector field, that means P maps to f of P given a vector field capital F. Now, P is from what? R of T, that is a point in your curve C. So, that means it is maps to f of R of T. And what I demand that f of R of T, that point has the same directions as the unit tangent vector. Now, if I take a point here, what is the unit tangent vector? That is this is the one, and this is my point RT. So, what is unit tangent vector? That is R prime of T. That means I demand that f of RT should be R prime of T. That is it. That is exactly I am doing. Okay. So, that is actually I have written also. So, f of p should be non-zero, number 1. Number 2, f of p has the same direction as the unit tangent vector Tp 2c at p. Now, given a curve C in R2, if I take a point in that curve C, that means I am talking about the point Rt, where R is the parameterization of your curve C. And what is the unit tangent vector? That is R prime t is the tangent vector, take the unit modulus, that is I am writing as T of p. So, that is exactly I have done, that is f of Rt is exactly equal to R prime of t. Okay. So, if this is the case, then that curve I will say that it is an integral curve. So, therefore, you have a vector field, you have a domain D, a curve in your domain which is parameterized by R. Suppose C is a curve in your domain D with the parameterizations R of t. I will say that it is an integral curve of my vector field capital F. If I take each point P in C, that means if I take a point RT in C, first point is that f of RT should be non-zero, and second one is that f of RT, that means the point I am associating via vector field capital F. What will be the vector I am associating at that point in your curve, which is nothing but R prime of t. Okay. So, that means that at each point RT in your curve, I am associating a vector what is called R prime of t, and that is nothing but I am saying that it is nothing but capital F of p or capital F of R of t. P and R of t both are same. If I take any point P in C which is of the form R of t, because R is a parameterization of your curve C, that is it. So, that exactly I am writing because I am associating with the tangent vector. No? So, therefore, obviously capital F is the tangent or sometimes called velocity vector field on the integral curve, because you have the integral curve, right, and for each point in the curve what vector I am associating? I am associating the tangent vector or sometimes the velocity vector. Okay. So, thus integral curves provide a geometric picture of a vector field. So, therefore, what point I am associating at each point in the curve? So, this is the one. If I take this point, so this is the one, this point, so this is the point, this is. So, that means each point, if I take this point, this is the one. So, at each point of my integral curve, I am associating a vector which is nothing but the tangent vector. So, therefore, if my curve C has a parameterization R of t, I am associating a point in my curve C which P is nothing but R of t, and what is the vector I am associating? Nothing but the tangent vector. That is why I am saying it is a F is a tangent or velocity vector field on the integral curve. So, for example, in a force field, integral curves are called lines of force. In fluid flow, integral curves of the velocity field are called what is called streamlines or flow lines. Okay. So, now I think it is clear what do I mean by integral curve. So, therefore, let F be a vector field in your domain. A oriented smooth curve C which is parameterized by R of t in my domain D. So, that means this is a curve in my domain D. I will say that it is an integral curve of my vector field, given vector field capital F, if the following condition satisfies. What are the points? If I take any point capital P in C, or if I take any point capital P which is of the form R of t, R, so that means P is equal to R of t for some t in C. So, two things will happen. First of all, f of p should be non-zero, and second one is that f of p, so that means what is f of p? F of p has the same direction as the unit tangent vector Tp 2c at p. That means, so if I have a point P in my curve C, that means corresponding point is Rt. So, what is the unit tangent vector T of p? What is the unit tangent vector? This is nothing but R prime of t. So, that means given point P in your curve C which is a subset of your domain D, I am associating a vector which is nothing but R prime t, and that exactly I have written f of Rt is nothing but R prime t. If my curve in my domain which satisfies these properties, that means f of Rt is equal to R prime of t, this curve is called the integral curve. So, therefore, sometimes since it is a tangent, I will say that it is a tangent velocity vector field of the integral curve. Integral curve provides a geometric picture of a vector field. In force field, integral curves are called lines of force. In fluid flow, integral curves of the velocity field are called the streamlines or flow lines. Okay. Okay, so I think I should stop here. So, this is the notions of integral curves. So, via integral curves also I can visualize what vector field I want to talk about or I am talking about. Okay. So, one way of visualizing vector field is the arrows. So, that means take a sample point, you draw a, that means at each point what vectors are there, which is the direction. So, that's the way you can have it, your visualization of your vector field. Similarly, instead of doing arrows, if I have a vector field with my domain D, and at each point, suppose my vector field is nice, suppose it is continuously differentiable, then at each point I will have a what is called curve, okay, passing through that point. But I am saying that that curve is an integral curve, provided at each point in that curve I am associating a vector which is nothing but a tangent vector and that curve. If that is the case, then I will say that that is an integral curve of that vector field. Okay. So, now I will show that given a vector field, that means continuously differentiable vector field, there is a way you can calculate the integral curve. I think that may be some partial differential equations or some differential equation you have to solve it, and then you will do that. Now, once I have the kind of integral curve at each point in my domain, through which I can also visualize, okay, that is the vector field I am actually talking about. Okay, I think I should stop here. In next class or next lecture onwards, I will talk about the how to calculate integral curves given a vector field is given, like if is a continuously differentiable vector field is given, then how to calculate what is called integral curve, of course in a special cases like in R2 and R3. I think I should stop here. Thank you.